anti-flip system is an active system to provide a safe and comfortable driving experience in four-wheeled vehicles.
Our system was designed to simulate a Ford E250 because of its higher risk of a rollover. The anti-flip system is expected to respond within 0.025 seconds, which is actually the average reaction time of a human. Also, it will detect the weight shift and compensate the vehicle accordingly.
This is a quick glance of the AFS layout. The force sensing resistor detects weight shift by providing varying voltages to the Arduino, which in turn instructs the servo motors via pulse width modulation to compensate for the weight shift. This all being done in 0.23 seconds, which is the servo speed per 60 degrees. The battery and voltage regulators allow enough current for the servo operation.
This is my Autodesk Inventor simulation of our actual prototype. This allowed us to compare the parts between each other. We can see the different measurements. We can see how it all moves together, and it allowed us to make sure the actual prototype will work in real life. This helped us transition into our actual product. Here's our actual prototype. You can see how very similar it is to the Autodesk Inventor simulation of it. Here's our servo motor. It's connected to this brass shaft, which is connected to a bearing, and that's JB welded to this linear bearing, and that's between two springs, which keeps it centered.
Now we're going to take a look at our simulations. This is a refined simulation of what we had previously. Here we can see the forces coming in from the left. We have our mass simulated, the friction from our linear bearings, the springs, the physical hard stops, and to the right you can see the four main things we're interested in, which is the position, the velocity, the acceleration, and finally, the most importantly, is the net force at the top right. Here we can see our input forces. The red trace indicates the force that is imparted on the car during a turn, and the purple trace is the response of our system. There is a delay of about 1/4 of a second. Here we can see the position response of our system. We have a steady, slow rise. We ended up choosing a different spring with 664 newtons per meter spring rate. This allows for a nice, smooth rise up until the very end of the external force, and then our system corrects once it has overcome that force. This final simulation is our most important one. This relates the net force imparted on our system to time. At 8 1/4 seconds, we see the moment where the force of our system overcomes the inertial force that is external. At 1/4 of a second later, we see that the system is trying to reach equilibrium, and it spikes up in the direction of the initial force. And 1/4 of a second later, it then returns to equilibrium. The total net force exerted on the system is approximately 1 Newton.
Weight is added to the left side to represent forces felt during a quick right turn. Weight is added to the right to represent forces felt during a quick left turn. The Arduino serial port shows the additional force in newtons to the corresponding sides. By meeting the speed and performance requirements, the AFS is a must for comfort and, most importantly, conservation of life.